Bum 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 bum.
Well, today we want to explore a little bit further something that we've done in class over the last couple of days, which is to work on estimating the area under functions. And there are many reasons why this becomes a useful thing for us to understand. We've gotten to see a few of those already, the connection between a velocity graph and the distance traveled. We can back that up a bit and say even the relationship between the acceleration and the change in velocity. So there's a connection there. But in engineering and other places, it's often useful to know, say, what the area of this particular curve might be. That can tell you something about the mass or the volume or the density of something. We can use these tools of knowing the area under functions to help us solve a lot of very important real-life problems. In class the other day, we looked at finding the area under the function 4 minus x squared. And we had a wide variety of different ways of doing that, primarily ways that related to breaking that area up into somewhat smaller areas somehow. And what we found was that people had various levels of success in the ways in which they approached the problem. But nobody really got a perfect result, at least not without some guessing or really sort of fudging things there, Ryan and Forrest. But we had some ways of computing areas, and that's a good start for us, and gives us some things to explore when it comes to more rigorous ways of doing this. So our method, this method we're going to use to estimate or find the areas of these curves, should have a couple of different characteristics that are very important. First of all, we would obviously like something that is efficient and accurate. There's sometimes a trade-off there, right? A couple of the ideas that we brought up in class were things that could become very accurate, but then were not very efficient. We had ways of doing this that were very efficient, but not necessarily very accurate. So there's a little bit of a trade-off between those two things. And by efficient, I mean it doesn't take an extended amount of time or effort to get the problem done. And by accurate, we mean that as we improve our method, our answer gets closer and closer. And that leads me to another method that we can talk about here, the fact that our results should be scalable, and our method should be scalable. And that is, if we want to make our result more accurate, there should be a way of doing that that is very systematic and doesn't involve having to completely redo or change the way that we do things. One of the things here that will become necessary then will be to basically only use one shape. Right? In our work, we use several different shapes to estimate the area under the parabola. And one of the things that's going to allow this to be a little bit more efficient and scalable is if we restrict ourselves to only one shape. One of the problems we had with some of the efforts that people attempted was that we found that, well, we can use this shape for this part and this shape for this part, and we can use this shape over here, and we ended up having a lot of different shapes. Unfortunately, that level of customization is not very efficient, and it's not very scalable. If we have to custom build our shapes for this particular curve or that particular curve, it no longer becomes something that is efficient and scalable. Well, it turns out that using one shape, we still have a wide variety of shapes to choose from, and in this course we'll get to see some examples using several other kinds of shapes. But for right now, the shape that we will use is a shape that is very easy to find the area of. We will divide our curve up, or the area under our curve, into a series of rectangles. So this is fairly efficient. If we look at an example here, this is fairly efficient as long as we come up with a reasonable way of dividing things up. So let's suppose that we want to find the area between, say, points A and B. We'd like to come up with as good an estimate as we can of the area under this curve, and we want to do that with rectangles. Well, clearly we could do this with one rectangle. right? We actually have several rectangles we could use. We could approximate this area with a rectangle that looks like this. So this is a rectangle that has the width of our base from A to B, and has the height of the function, the height of the value here is the value that we have at the left end point of our region that we're trying to find the area of. Obviously, this area will be too large. In this particular case, we can see that it takes in a lot of area that is not part of the graph. We could do something where we use the right endpoint and estimated this with one rectangle here. Okay, and that would also be a way for us to determine the area. Now this one maybe is an even better approximation to the area in this particular case, right? So there are still things about our method that can depend on the actual case we're doing, but one rectangle, we can come up with an estimate. Again, not necessarily a good estimate. Our percent error may be large, but we can still determine a relative area here. Another possibility would be to look at the midpoint of our region here and determine what the function is doing here and come up with another value for the area, another method. This is a reasonable way to do this. We can take the left end point of our rectangle, the right end point of our region, or the midpoint of our region. What we really need is we need some way to define the height of our rectangle. The base of the rectangle is fixed by the width of our region, but we need some way to determine the height. And the way we determine the height has to be based in some way off of the function. We can look at the left end point, the right end point, or the midpoint of our region to determine that value. But the area then becomes a simple matter of working out the formula for the area. So our area estimates here become f of a, the height of the function at the left-hand side, times b minus a. This is simply the width, right? We have here the height and the width of our rectangular area. Another estimate that we came up with was f of b, the right end point, times the width of our function, region. And the third one was the function value at the midpoint, again, times the width of our region that we're looking at. So here we came up with three different possibilities for the area estimate of our function. We could do things like average these together, or some other method to try and come up with a more reasonable estimate or reduce our error somehow. But this is also a very scalable method, right? This is also a very scalable method. If we want this to be more accurate, if we would like this to be a more accurate expression, one of the things that we can do is simply add in more rectangles. So we'll go ahead and look at this with maybe some additional rectangles in here. I'll try and reproduce the curve here. So going from A to B, again, if we would like to estimate the area under this function between A and B, one of the logical things if we want to do our division up uniformly in a systematic way would be to simply divide this function up into two pieces along the midpoint of our region. Now we can make a rectangle here and a rectangle here. These two rectangles are based off of the left endpoint, so the height of our function at the left endpoint tells us the height of our rectangles, and then we simply have to add those together. So we could have f of a times a plus b over 2 minus a. This is the height times the width. This would be for this first rectangle here. Plus we could sum then the height of our second rectangle, which would be f of a plus b over 2. That is just the height at this point right here times the width of our function here, b minus a plus b over 2. And this would now be an estimate of our area. And you can see that it's certainly a better estimate than the estimate we used with the left endpoints was initially, because we have basically cut out this area, which we certainly didn't want in there to begin with, because that's mostly empty space and not part of the region that we're interested in. We could do the same thing with our right endpoints, or we could come up with the midpoints of our regions as well. And again, this is scalable. If we would rather have 3, let's go ahead and take a look at what happens if we have 3 regions. If we divide our function into 3 regions and find the estimate of the area there. So here is our point. Here are our points A and B. And now what we would like to do is divide this up into 3 regions and estimate our area based off of these 3 regions. Now the width of every region is going to be the same if we're systematic about things. Each of these is simply going to be the entire width of the function divided by 3, since we're dividing this up into 3 intervals. And then we have the points A. This point right here, this x value will be A plus B minus A over 3. That's simply A plus the width of this region right here. This point right here will be A plus 2 of these B minus A over 3 widths. And then the last one here will simply be B. And we could go through now and find the values of the functions at various points. Let's say, for example, that we wanted to find the area of the rectangles that are based off of the right endpoints this time. So the right endpoints means that for the rectangle that has this base, I'm going to use this value. So this is one rectangle here. For the rectangle with this base, I'm going to use the right endpoint here. That will be this area. And for this rectangle here, if I use the right endpoint, that will be this one right here. So we can estimate this area. And again, you see we have a region that is not counted. We have another region that is an overestimate on this rectangle. But we can argue that as we go through and do this, as we choose rectangles and as we start to make more and more rectangles, we end up with a more and more accurate expression for the area of our object. We started with 1 rectangle. We went to 2 rectangles. Now we've just looked at 3 rectangles. Hopefully you can see where this is going.